In our previous lectures, we have seen how to utilize symmetrical components to analyze unsymmetrical faults in an otherwise balanced power system. Now, today we will study how to analyze any unbalanced three-phase system using symmetrical components. In network theory, usually whenever we deal with the three-phase system, either those are balanced or we deal with them if they are unbalanced using direct KCL or KVL. Now, we will try to utilize the concept of symmetrical components to analyze the circuits which are three-phase and have unbalanced load. Let us see how to analyze them. Now, I am going to take a very general case. Let us we have a series impedance load. This is point A dash. Let us say this impedance is ZA. Similarly, another load in phase B, let us say it is ZB, B dash. Another load in phase C is ZC, C dash. Now, let us say the current is IA, the line current in phase A. The line current here is IB and in it is IC. Now, in our one of the previous lectures when we were studying the sequence networks or sequence component for transmission line, we have seen that whenever the load is unsymmetrical, then the sequence networks are not decoupled. That is, there will be a coupling between the sequence networks. So even if this network is not having mutual coupling, even then there will be a coupling between the sequence networks, because ZA is not equal to ZB is not equal to ZC. So this system is not a balanced one. So when we will derive the equations, as we have already seen in our previous lectures also, that the sequence voltage and currents will not be decoupled. These will be interdependent upon each other. That is, the positive sequence current will create a voltage drop of negative sequence, zero sequence and positive sequence. Similarly, the negative sequence current will create a voltage drop of positive sequence, zero sequence and negative sequence. Similarly, the zero sequence current will also create a voltage drop of zero sequence, positive sequence and negative sequence. So you see, unlike the case of balanced system in which a positive sequence current used to create only positive sequence voltage drop, in an unbalanced system it will also create a negative sequence as well as zero sequence voltage drop. So in this way we cannot show various sequence network independently. So let us see how to proceed further in such a case. Now, I can write the equation of various voltage drops VAA dash is equal to ZA IA, VBB dash is equal to ZB IB and VCC dash is equal to ZC IC. So, in this way I have written normal KVL equation. Okay. Now I can write them in the matrix form also, like this is the voltage drop vector VA dash, VBB prime, VCC prime is equal to ZA 0 0 0 ZB 0 0 0 ZC equal into the line current vector IA, IB, IC. Now this is the equation, the same equation in matrix form. Now what we will do, we will convert the voltage drops into their sequence components and line currents into their sequence component. So we can write this vector as 1 1 1 1 a square a 1 a square VAA dash 0 VAA dash 1 VAA dash 2. Zero sequence, negative, positive sequence and the negative sequence. Similarly, it is equal to, I will write the impedance matrix here, ZA, ZB, ZC, all other entries being 0. Okay, now similar to this, we will also write IB, IA, IB, IC into their equivalent sequence components. Now it is again A times IA0, IA1, IA2, that is 1 1 1 1 A square A 1 A squared is equal to into IA0 IA1 IA2. Now we want to determine the value of various voltage drops sequence component. Okay, so what I will do, I will pre-multiply this equation by the inverse of this matrix. This matrix is A matrix, so I pre-multiply with A inverse. So it will just convert into a identity matrix or unity matrix 1 0 0 0 1 0 0 0 1 multiplied by this matrix, and the resultant will be simply VAA dash 0 VAA dash 1 VAA dash 2 is equal to 1 by 3. The inverse of this matrix is 1 by 3 1 1 1 1 A squared 1 A squared A into ZA ZB ZC 0 0 0 0 0 0, and again this is A matrix 1 1 1 1 A squared A 1 A squared into IA0 IA1 IA2. Now if we do this matrix multiplication, then we will get relation between various sequence component of voltage drops and sequence component of the line current. Okay, so I will do multiplication here. VAA dash 0 VAA dash 1 VAA dash 2 is equal to 1 by 3. Let us first do this multiplication, A inverse into Z. We will do this multiplication first. So 1 ZA plus 0 plus 0. Similarly this ZB, similarly this is ZC. Okay, this is the first row. Now let us do for the second row. ZA 0 0. Now for the second column of second row 0 AZB. For the third column of second row it will be A square ZC. Now let us see the third row. First column will be ZA, second column will be A square ZB, AZC. Okay, now we will post multiply this with A matrix. IA0 IA1 IA2. Okay, so we will do this multiplication here. We get VA0 VAA dash 1 VAA dash 2 is equal to 1 by 3 is outside. ZA plus ZB plus ZC. ZA plus ZB plus ZC. Okay. Now next, ZA plus A square ZB plus AZC. ZA plus A square ZB plus AZC. Now the third column of first row, ZA plus AZB plus A square ZC. ZA plus AZB plus A square ZC. And here is the current vector IA0, IA1, IA2. Okay. Now the second row, ZA plus AZB plus A square ZC. ZA plus AZB plus A square ZC. Okay. Now let us see the second column of second row. ZA plus A cube ZB. Now A cube is just equal to 1, so I will just write 1 ZB. Similarly, the third, A cube ZC plus ZC. Now the third column of the second row, ZA plus A square ZB plus A4 ZC. Now A raised to power 4 is equal to A only, so I will write it directly, ZA plus A square ZB plus AZC. Similarly, we can write the third row, ZA plus A square ZB plus AZC, and ZA AZB plus A square ZC. Okay, and it is equal to ZA plus ZB plus ZC. Now let us see how to solve this thing or analyze these equation further, that we will see in the next slide after erasing this. Now I will open these matrices and I will write the various component sequence voltage drops. VAA dash 0 equals to ZA plus ZB plus ZC divided by 3 into IA0 plus ZA plus A square ZB plus ZC divided by 3 into IA1 plus ZA plus AZB plus A square ZC divided by 3 into IA2. Okay, now let us write the positive sequence voltage drop VA-1. It will be equal to ZA plus AZB plus A square ZC divided by 3 IA0 plus ZA plus ZB plus ZC divided by 3 IA1 plus ZA plus A square ZB plus AZC divided by 3 IA2. Similarly, I can write the negative sequence voltage drop VAA dash 2 is equal to ZA plus A square ZB plus ZC AZC divided by 3 IA0 plus ZA plus AZB plus a square zc divided by 3 ia1 plus za plus zb plus zc divided by 3 ia2. Now these three equations we have got. Now let us first see various components of this matrix. This is 1 1 1 2 1 3, 2 1 2 2 2 3, 3 1 3 2 3 3. Now you can clearly see that 1 3 is not equal to 3 1. Similarly 1 2 is not equal to 2 1. So you can clearly see that Z12 is not equal to Z21, Z13 is not equal to Z31, Z23 is not equal to Z32. So you see that the network is not reciprocal here. Okay, so the sequence, even if this three-phase network is bilateral or reciprocal, even then the sequence network is not following that property. Okay, so this is a very peculiar thing about this network, and I already told this in my one of the previous lectures. Okay, now let us see how to memorize this equation. It is actually not required to memorize, but it is very easy to write this equation without going into the matrix multiplication. Now let us see how to do that. I will write this ZA plus ZB plus ZC, which is there, as ZS. ZS equals to 1 by 3 ZA plus ZB plus ZC, and it is called self impedance of the sequence current, okay, or sequence network. So what does it mean? You can clearly see that the zero sequence voltage drop, or the component of zero sequence voltage drop which is created by the zero sequence current, is depending upon this value, which is Zs, which I have written as Zs. Similarly, the component of positive sequence voltage drop created by the positive sequence current is again depending upon Zs only. Similarly, the component of negative sequence voltage drop which is created by negative sequence current is depending upon Zs only. So we can easily say it to be self-impedance of the sequence network. Now let us say I will write Zm1 is equal to 1 by 3 Za plus a Zb plus a square Zc, and Zm2 equal to 1 by 3 Za plus a square Zb plus a Zc. Okay, so I will replace these names and I will tell you how to write this equation directly. So let us replace this. I will erase this and write it as Zs. Similarly, I will erase this and I will replace it with Zm2. And I will erase this and replace it with Zm1. So now you see that to memorize this shortcut to write this equation, there is a method. If I add the subscripts, this is 1 and this is 2. 1 plus 2 is equal to 3. So as we know, a cube is equal to 1 only. So this 3 pertains to 1 only. Oh sorry, a cube. Since a cube is equal to 1 only, and since it is nothing but a complete circle in the 360-degree scenario, so it is equivalent to writing this thing equal to can be remembered as equal to be 0 only. Okay, that is, it is not going to create any change. So this 1 plus 2 is again 3 is equivalent to 0 only. This 0 of the zero sequence voltage drop. Similarly, this subscript Z2 and 1, 2 plus 1 is again 3 and it is equivalent to 0 only. And now there is no subscript here, this is 0, so 0 is equal to 0 only. So in this way I can memorize various sequence impedances and there is relation with the sequence currents. Now let us write this equation directly without even seeing this. I will erase this and we will try to write it directly from this shortcut which we have seen now. This is VAA-1. Here it is A0. So some subscript should come which should be equal to 1. 0 plus 1 so that it is equal to 1. So I will write ZM1 here. Now here it is IA1. 1 plus 0 should come so that it is equal to 1. So it is ZS. Now this is IA2 here. Now what should I do such that equivalent to 1 should come? Now as I have told, A4 goes only directly equal to A only, so it is equivalent to 1. Okay. So A4 equals to A1 only. So if I put an impedance with subscript 2, then it will give me value equivalent to 1 only. Okay, so I have written this equation. Now let us write the third equation directly. IA0, 0 plus 2 should come, ZM2 plus ZM1, IA1 plus IA2, ZS. Okay, so in this way we can directly write these three equations. Now how to memorize this, what is ZM1 and what is ZM2? It is very easy. ZM1 is called the mutual positive sequence impedance and ZM2 is called the mutual negative sequence impedance, and it is similar to the positive sequence current and the negative sequence current which we usually derive. Okay, so in this way I can easily remember it as mutual positive sequence impedance, mutual negative sequence impedance. Okay, now in this way we can memorize these equations for static unbalanced three-phase load. Now in the next slide what we will do, we will connect these 3 points and name them as neutral. Okay, so in this way we will make a star connected unbalanced load and we will try to analyze that scenario in the next slide using these equations only. Now let us analyze the scenario given in this figure. Here what I have done, I have shown a 3-phase synchronous generator which is generating balanced voltages. Okay, let us say it is grounded through some impedance ZGN. Okay, now here is a load, star connected load which is unbalanced, that is ZA is not equal to ZB is not equal to ZC. Now we want to analyze such kind of scenario using sequence component theory or the symmetrical component theory. Okay, we can analyze it using network theory directly just by writing KVL equations in each loop. Okay, but let us see how to do such kind of calculation using symmetrical components. Now it is nothing but the scenario in which A dash, B dash and C dash have been connected to make a neutral N. Okay, so VAN can be written as VAN0. Let us write first the zero sequence component, ZS IA0 plus ZM2 IA1 plus ZM1 IA2. VAN1 can be written as ZM1 IA0 plus ZS IA1 plus Zm2 Ia2, and Van2 can be written as Zm2 Ia0 plus Zm1 Ia1 plus Zs Ia2. This we have written from the previous slide only. Okay, now this is a balanced circuit up to this point. Okay, the unbalance is here. This is the unbalanced load. Now we know that, let us say this is capital point N, this is small n point. Okay, again this will be Van, this is Va small n. Here is voltage Van, and here is voltage Van. Okay, now since it is a balanced system, here I can write Van1 positive sequence component equals to Ea minus Ia1 Z1. It is nothing but the positive sequence impedance of the balanced network. Similarly, Va2 is nothing but minus Ia2 Z2, and this is Va0 will be minus Ia0 Z0. Now this Z0 is comprising of two impedances, the Z0Z, the generator zero sequence impedance, and the sequence impedance of the transmission line, plus three times of ZZN. Okay, so this is comprising of these two impedances. Now what we will do, we will see what is the relation between these two voltage drops. That is, we will try to see what is the relation between Va capital N1 and Va small n1. Let us visualize this. First we should know that this Z1 is comprising of two impedances. Since it is a balanced network up to this point, this Z1 is comprising of the positive sequence impedance of the generator and the positive sequence impedance of the connecting transmission line. Similarly, this is comprising of the negative sequence of the generator and the negative sequence impedance of the connecting transmission line. And similarly, it is the zero sequence impedance of the generator plus 3 times of ZGN and this zero sequence impedance of the connecting transmission line. Now let us see what is the relation between these two. Now imagine that only positive sequence currents are flowing. Okay, so when only positive sequence currents are flowing into the system, the balanced positive sequence current, IA1, IB1, IC1. Okay, now we know that IA1 plus IB1 plus IC1 is equal to 0 because it is a balanced set. So there will be no current in this impedance. Similarly, there will be no current in this impedance. So the voltage drop here up to this point and the voltage drop from here up to this point will be equal. That is, it is not going to depend upon the path. Okay, so VAN1 is equal to VAN small n1. Okay, so I will put this thing VA capital N1 equal to VA small n1. Okay, so we can see that EA minus IA1 Z1 is equal to Zm1 Ia0 plus Zs Ia1 plus Zm2 Ia2, or EA equals to Zm1 Ia0 plus Zs plus Z1 IA1 plus Zm2 IA2. Now similarly, let us see the relation between VAN2, the capital N2, and the relation between VA small n2. Now let us imagine only the negative sequence current are flowing in the network. Then we know that IA2 plus IB2 plus IC2 is equal to 0. So again the similar relation will hold, that is these are equal to each other. So I will put this value equal to this one. So I will get minus IA2 Z2 equals to Zm2 IA0 plus Zm1 IA1 plus Zs IA2, or I will take this side, 0 equals to Zm2 IA0 Zm1 IA1 plus Zs plus Z2 IA2. So let us say this is equation 1, this is equation 2. Now let us see how to find the relation between the zero sequence voltage drop. That is VA capital N0 and VA small n0. Now the voltage drop of this point to ground, since the zero sequence current IA0 plus IB0 plus IC0 is not equal to 0, it is rather equal to 3IA0. So current will flow from here to this point to ground. So it will be having a path from these neutral connections. Okay, so you see that VAN0 and VA small n0 can be written as, these are equal because this point to ground and this point to ground are equal. Okay, so minus IA0 Z0 will be equal to Zm2 Zs. Now in that derivation in previous slide we have not considered this ZLN. So for the flow of zero sequence current it will appear as 3 times of ZLN. Okay, so for zero sequence current it will be having 3 times of ZLN also into IA0 plus Zm2 IA1 plus Zm1 IA2, or we can take this on the right hand side, it is equal to 0 equal to Zs plus Z0 plus 3ZLN into IA0 plus Zm2 IA1 plus Zm1 IA2. Now let us say this is equation number 3. We have got 3 crucial equations for such kind of network and I will rewrite them in the next slide after erasing these. Now I have written these 3 equations here. You can see these 3 equations are very crucial for solving this network. Now let us say that this neutral is not connected. Okay, so the zero sequence current cannot flow because it is not having any path to flow. So the IA0 will be 0. So these equations will transform into EA is equal to Zs plus Z1 IA1 plus Zm2 IA2. This is equation, let us say 4, and 0 equal to, this will be not here, this will not be here, Zm1 Ia1 plus Zs plus Z2 Ia2. This is equation number 5. Now this term will not be here. However, the potential of VA and the zero sequence component can be written as VAN plus VNG. Okay, that is the voltage of point A with respect to ground. The zero sequence component can be written as the zero sequence component of VAN and the zero sequence component of VNG. Now we know that it is only zero sequence component only because it is created by the zero sequence current if they have any path. Okay, so since these are not having any path, this term is equal to 0. But there is an issue now, that this VNG0, we don't know what its value can be, because there is no zero sequence current flowing, it is 0, and this impedance is infinite with respect to ground. So the voltage drop is 0 into infinity. It is not able to be determined using this thing. Okay, however, there can be a value. So let us say it is having some value minus Vn. Okay, minus Vn is having its value is equal to VNG0. Okay, so I will take it this side. So what I will do, I will take its effect I will take in equation number 3, because Ia0 is equal to 0. I cannot calculate it, but it can be there. This point N can have any voltage with respect to ground which is not able to be calculated using these equations. So let us say I write it as only Vn, the voltage of point N with respect to ground, plus Zm2 Ia1 plus Zm1 Ia2. Let us say this is equation number 6. Now upper 3 equations are when there is a neutral connection, and lower 3 equations are used when there is no neutral connection. Okay, so now from this I can find what is the value of Vn. It is nothing but equal to minus Zm2 Ia1 minus Zm1 Ia2. So now we can find the value of the voltage of this point N with respect to ground using this. Okay, now from equation number 4 and 5 we can find the value of Ia1 and Ia2 in terms of Ea and the various impedances. Ia1 can be found out as Ea Zs plus Z2 Zs plus Z1 Zs plus Z2 minus Zm1 Zm2. Similarly, I can also find Ia2, and I will leave this as an exercise for the students to find its value. Now in the next slide we will use these equations, equation number 1 to 6, this let us say equation number 7, and let us say this is equation number 8, and let us say this is equation number 9. I will use these 9 equations to solve a numerical example of unbalanced load for by the method of symmetrical components. Now let us see the numerical example of a 3-phase unbalanced system. In it, what I have shown, that there is a synchronous generator with Ea is equal to 1.3 per unit, that is no node voltage generated, and the synchronous reactance is J1, the negative sequence reactance is 0.3 per unit, the zero sequence reactance is 0.05 per unit. Okay, and let us say it is also isolated, and we are given a star connected unbalanced load. ZA is equal to a purely resistive load of 1 per unit, ZB is equal to ZC equal to purely inductive load of J1 per unit. Now we need to find various currents and voltages. Okay. Now, in our previous slide, we have seen that we need to find various impedances ZS, Zm1 and Zm2. Now Zs is nothing but 1 by 3 Za plus Zb plus Zc. So it will be equal to 1 by 3. B and C are equal. Zb and Zc are equal. So 1 plus J2. And it comes out to be 0.333 plus J 0.667 per unit. Zm1 is equal to Za plus A square Zb plus A Zc. Both are equal. Then A square plus A is common. So it is equal to -1. So I can write it as Za minus Zb. Similarly, Zm2 is equal to Za minus Zb. So you see that both of these are equal. Whenever two impedances are equal in a unbalanced three-phase star-connected load, we will find that Zm1 is equal to Zm2 equal to Za minus Zb. This is a very general case. Okay. So it is equal to 1 by 3, 1 minus J1, 1 by 3, 1 minus J1, and it comes out to be 0.471 angle minus 45 degree, 0.471 angle minus 45 degree. Okay. Now we are given value of Z1, Z2 and Z0 also. Z1 equals to J1, 0 plus J1, Z2 equals to J 0.3 and Z0 equals to J 0.05. Okay, and EA equals to 1.3 plus J0 per unit, and we are taking on line to neutral base. Okay. Now we can find IA1 directly using the formula or the equation number 8 of the previous slide, or equation number, I think it was 7 or 8 only. It is equal to EA Zs plus Z2 Zs plus Z1 Zs plus Z2 minus Zm1 Zm2, and it comes out to be, on putting various values, it is 0.715 angle minus 73 degree, and IA2, although I have not derived the final value, but I will write it directly here. I have left it for this student, minus EA Zm1, and denominator is same for them, Zs plus Z1 Zs plus Z2 minus Zm1 Zm2. So it comes out to be 0.329 angle minus 9 degree. Now you see that there is no neutral connection. So IA, the current in the line A, is equal to IA1 plus IA2 only. And it comes out to be 0.907 minus 54 degree per unit. Now similarly we can find IB also. IB equals to A square IA1 plus AIA2, and it is equal to 0.947 minus 150.13 degree per unit. Similarly, IC equals to AIA1 plus A square IA2, and it comes out to be 0.388 angle minus 43.7 degree per unit. Now I know the value of IA, IB, IC. Now I can find VAN, VB and VCN. Okay, so VAN can be written directly as IA into ZA. This is IA and this is ZA. So IA into 1 per unit, it is equal to 0.907 angle minus 54 degree per unit. Similarly, VBN can be found out, VCN can also be found out. IB into ZB, and it is equal to 0.941 angle 947 angle 240.1 per unit, and VCN multiplied by J1 only, IC into ZC, which is J1 only, it comes out to 0.388 angle 113.7 degree per unit. Okay, so in this way we can find VAN, VBN, VCN. Now we need to find the potential drop between, or potential difference between this point N and this point capital N. We need to find VNN. Now in this circuit, what is VNN? It is nothing but, let us say I ground this. Okay, so now you can clearly see that VN is nothing but VNG only. If I don't ground it, it is VNN only. So it is very easy to see that from our previous slide, equation number 7, I can see that it is nothing but minus ZM1 IA2 minus ZM2 IA1. Now ZM1, ZM2 I have, IA2, IA1 also I have, and it is equal to 0.43 angle 81.2 degree per unit. Now all of these voltages are on a base of line to neutral voltage. Okay, so in this way, instead of using KVL and KCL in various loops like this loop or mesh, I have utilized the theory of symmetrical components in deriving or solving such a numerical example of circuit theory.